Okay, I'll just record here and
Okay.
Dennis can join soon.
Okay, so this is, I guess I'll just start. Dennis will come in a minute. So this is part 2 of my space and logic talk. So a few of you weren't here a couple weeks ago when I did the first one. This one I think will be a little more concretely applicable to what we're doing. But it builds a little bit, but hopefully if anyone has questions or is confused, just let me know, since I am kind of jumping around a bit. But generally I want to talk about ultrafilters and model theory. First, I want to just, because I think last time we had some confusion with the Yoneda lemma, and it's tricky. There you go. Okay, so this is a recall of the statement of the lemma itself, but I made this little picture kind of based on the one from that blog that I sent you guys, that if you're curious, I recommend you read.
It's amazing, yeah.
It's very good. There's 3 parts they really explain what's happening in the Yoneda lemma, kind of like step by step. So going over it again, just the statement is that if we have any category X, any category C, and we have an object in it. And we also have a contravariant functor. There's also a covariant version, just take away this op, and it works equivalently, so that's not really an issue. But the idea is that if we want to understand an object X in the category, but this is a very general concept, so it could really work, I guess, anywhere. The idea is that we want to understand all of its relationships with objects outside of it, either relationships going out of it or relationships going into it. So what it's saying is that if I have X, if I have any contravariant functor, F, it identifies exactly the set of natural transformations from this representable functor, this C blank X, and F. Okay, so that seems kind of confusing. But if we remember from last time, C blank X, that's the representable pre-sheaf. We can really interpret it as X properly. That's really, we'll see after this, really what the Yoneda lemma says. But even more is it gives a way to completely characterize any functor by the natural transformations from the representable functor. So what this does, because you can imagine the space of natural transformations from this functor. So this, just to remember, the C blank X is a functor from C op to set. So what it does is it takes in a value of your category, and it gives you all of the relationships. In this case, it's going to be all of the maps into the object X. But what it's saying, right, is that the set of natural transformations from this representable functor to an arbitrary functor, it doesn't matter which one, is going to be exactly fx, if you just apply the functor to your object X. So it's a very striking thing. If you want to hear, this gives a bit of a picture of what's actually happening. So if we have a category here on the left, any functor. So what it does is it sends an element of fx, so that's going to be C, this purple C on the right. That is going to get sent to this natural transformation eta. Okay, without the subscript. When you put in the subscript, what it's doing is it's basically focusing in on a specific object Y that I'm going to consider relations with. Okay, so I'm going to think of the relationship from Y to X, in this case, G. So what's G doing under this functor, under this natural transformation? G is going to get sent simply to the post-composition of G with the functor F. So it seems kind of simple and trivial. And the thing is that kind of at the core of many deep theorems in category theory, and like there's a joke that basically anytime you have a theorem in category, in like pure category theory, or even not in just applied mathematics in general, very, very often it can get, I guess, filtered down to just being a consequence of this Yoneda lemma. Which really, really we want to say is I want to stress this again and again, that it's we understand an object by its morphisms in and out of it in general. And then, okay, so we have a couple, these are the, I guess, two important corollaries from the Yoneda lemma that we really want to keep in mind. The first is about the Yoneda embedding, which this is the functor that sends an object to its presheaf, okay? So according to the Yoneda lemma, it doesn't take that much work to prove that this embedding is a fully faithful functor. Okay, so a recall, I guess, a bit on functors is that in general, a functor doesn't act well on the objects of the category. But how we characterize a functor is how it generally acts on the morphisms. So when it says it's fully faithful, with the full is like a surjective and the faithful is like an injective. So it's whether it hits everything and whether two morphisms get sent to the same one. But it's on the morphisms is the important part.
Mm-hmm.
So this induced map from Ham x to y, so it's going to take in a morphism. So it's an induced map from this functor. So you see, normally you just plug in an object and get this representable presheaf. But if we plug in in an arrow or a function or whatever, a morphism, then we're going to get a natural transformation between the representable functors. And that, in fact, this is a bijection, and it's written F lower star. It's, I believe, the pull back, which is going to be basically doing right here, as we saw. It's going to be a post-composition of F. So a simple thing, but this can completely characterize how objects work. So I guess from this corollary one, we can really say that the representable functor, right, is, or representable presheaf also, is the same as the object F. So really there's not a difference, but we can even go farther. The corollary two, so if we take, it's pretty easy to see if I go back. If you just take an F, if you put the representable functor for some object Y, so it'd be the natural transformations from C blank X to C blank Y, is going to be isomorphic. If you just plug this in here, we get this ultimately. We get X is going to be equivalent to Y, if and only if its representable presheaf is our equivalent, or if they're representable co-presheafs, which are these ones, are equivalent. So this really gives us the full thing to show that if we want to understand an object, we look at all the maps in and out of it. Okay, it's a very general, I guess, almost a cliche thing to get from it, but it's in the math itself, it's a deep result. But using this, I want to give maybe a little bit of intuition for how this actually helps, and maybe actually will help us. So this is some mathematical examples. But this can be used, these presheafs, basically to probe into different kinds of spaces. For example, if we look at all of the maps from a single point into a set, that collection of maps is exactly going to have the cardinality of the space, right? Because you're just mapping a single point into any, so there's as many as there is the cardinality. So quite simply, you can just say that X and Y have the same cardinality if and only if, when we plug in the 1 point space into these representable presheafs, if those have the same set points. So this is a way of like categorifying a lot of like traditional math concepts. Another one obviously is a path space, where you can look at all of the functions into a space from an interval and look at to what degree they're equivalent as path spaces, and equivalent in terms of how they can support different paths and which paths exist. So for example, the real line will have a very, well, let's say an interval. An interval will have a pretty small path space. But if we look at like the plane, it's going to be quite large. And loop spaces, which if anyone is familiar with homotopy at all, or the fundamental group, that's exactly what this is. We can compare spaces by how a loop or a circle maps into it, right? So what this set of transformations from the circle, this is what S1 is. S1 is just the circle into some space. They're going to be basically the paths up until pushing them around, and then we can say that those spaces have the same fundamental group, or the same path loop space, if and only if their fundamental groups are the same.
So I mean, just to see if I'm following, sure. Generally, it's like, for example, in the case of the cardinality, which is the simplest one, right? So if I have a set here with, I don't know, 3 points. I mean, sure, there are three arrows like this, right? I don't know what's in X, and I don't know what this is, but I capture information simply by looking at the amount of arrows, right? So it's the idea that exactly. I don't need to know that much about this or about this, that this here in the middle actually captures all the information that I'm interested in, if I do it properly.
Yeah.
Right? If I code this in the right way.
Yeah. But not necessarily just the amount of arrows. It can also be the structure of the space of relations.
But the space of relations here.
Yeah.
Right?
Yeah. So
the
like,
space of the morphisms, not the space of the things being related. Right?
Yes, exactly.
I think that's the big intuitive jump, right? How the hell,
so,
looking at the structure of the morphisms, can you learn so much about the things being transformed?
Yeah, well, turns out you can learn everything.
Yeah.
Well, at least theoretically.
That's the crazy thing. Yeah.
So we'll get to that. But the important thing to keep in mind when you do this kind of thing is that every time you do one of these, like you probe a space, you're always kind of getting a perspective of the space up to some limitation. So for example, in the cardinality example, it's only counting the physical quantity of the stuff in the space. There's nothing about how it's connected or the topology of it. But if you go to something like a loop space, it captures, or the fundamental group, it captures a lot of information about the space. Maybe let me draw a little bit I have this little tablet thing, so it should make it easier. I'm gonna take up here, draw. Okay, yeah, so for example, just with the fundamental group, just because I think it's easier to see. If we have a sphere, oh, there you go. Okay, so this is a sphere. Okay, so you can, if you take a loop, let me change to maybe green. Okay, so imagine if I take a loop on a sphere. So this is an example of one of these, right? Really, it's just a circle. Oh, that's a bad circle. S1. And I'm mapping it into here. The thing that you notice about the sphere is that anytime you have a sphere, you can actually contract this to a point, and it's never going to be stopped, right? Well, what this means is that the fundamental group, right? So it's written like this, pi1. So if you see this in topology stuff anywhere, of S1 is just trivial. So I guess it's just 0 or whatever you want to call it. It's just gonna be the one element group, because when you look at these spaces up to homotopy means if I take this loop and then I kind of push it a bit, right? Maybe push it so maybe now it's extends out this way or something. I don't know, right? As long as it doesn't cross any boundaries or any points, these are going to be said to be equivalent, okay? So in the sphere, for example, all of these loops are exactly equivalent because every single one can be contracted to a point. Okay, so that's that. But for example, let's say if we look at a torus, a little donut shape, it becomes a lot more clear that, for example, look, I can take a loop and I can loop around one way this way. Oh, make it look like it's actually going all the way around. I can loop kind of around one ring of the donut, or I can go around this way. I can do this as well. And these two loops are actually not equivalent at all, and they can't be contracted. And it turns out that for the torus, you have pi1 of t2, that's going to be the integers squared, which means that there is integer squared number of homotopy classes of loops on the sphere. So what that means in this case is I can loop one time this way, or I can loop one time this way. I can also loop the other direction, or the other direction here, or I can loop as many times as I want. So I can loop twice and come back. But however many times I loop is completely characterized by some point in the integers squared. So a pair of integers. How many ways I loop around this way and how many ways I loop around this way.
Yeah, and in the first one, it's also Z, right? The homotopy of S1 is also Z because, oh no?
No. The homotopy group of the sphere is trivial because everything can be contracted to a point.
Okay,
of a circle will be Z, yeah.
I see, okay.
Yeah, so a circle can loop around itself in either direction as many times as you want. So that's gonna be, but on the sphere itself, which is a weird fact, and if any of you have heard of the Poincare conjecture that Grigori Perelman proved like 10, 15 years ago, something like that, is exactly this question, but about the three sphere. The question was, is the three sphere, a sphere in three-dimensional space, the only homotopy space of 3 dimensions that has where everything contracts, where every loop contracts. So it's true on the sphere, on the normal sphere that we think of, but on the 3 sphere, it was a hard problem for a long time, if that was the only one. So ultimately, that's a question of, can I figure out if something is a sphere only by looking at the loops, right? So sometimes it's enough. For example, right here on the sphere, if I take a space, and if I know it's a surface, okay, I already know it's a surface for some reason. If its fundamental group is trivial, it has to be a sphere, which is pretty nice to figure that out if you can compute that. So it's ways of probing into different spaces. But it's always important to understand, I guess, like the limitations of this probing. So these loop spaces are very important, and they're a deep, deep field and very difficult to compute in general. But generally, if you want to prove, for example, 2 different spaces are actually different spaces, if you don't know if they're the same or not, you can prove that their fundamental groups are different, and you'll know that they're not the same space.
But for example, in the case of loop space, it's like we have a loop here, and we have some space we don't know of, and we know that if ultimately all these arrows are the same arrow, that's a trivial.
Yeah, so what we're saying, if they're the same arrow up to this thing called homotopy, which is just kind of pushing them on the surface or in the space. Yeah.
So if that's the case, exactly. then knowing this about the arrows means we know it's a sphere. On a surface, on a 2-dimensional surface, turns out, according to Poincare's conjecture, in a 3-dimensional space, that is also true. So that's good. Here, let me just clear this out. Okay.
And then so that this is all ways of probing spaces by looking at maps into them. We can also look at maps out of them. These are just a couple. There are definitely more examples out there that may be better ones, but we mentioned this one last week about a space being connected. So space X is connected if every continuous map to 0, 1 is constant. So this is another way of characterizing a space by connecting this just by any map into this just simple 2-point space. If we go further, right, we can actually, if we have every map into this thing is called the Sierpinski space. It's just the simplest poset you could maybe ever imagine that looks like this. Just a 1 and a 0. But it's just giving the topology saying that 1 is open and 0 is closed, I believe. But it gives it a poset structure. And if I take the pre-image of 1 of any map of this, because of properties of continuous functions that if people want to get into the specifics about, we talked about last week, each map like this will actually represent an open set in the topology on X, if X is a topological space. Meaning that the set of all of these maps, so if we look at this, if we look at Ham from X to this Sierpinski space, is actually the topology of the space itself. So this is another way of like defining a topology by taking a collection of maps onto the Sierpinski space. So basically almost everything can be kind of like categorified in this way by looking at things by their relations, by choosing suitable relations and suitable universal properties. Let me turn this around. Okay, so I have a few, I guess, lessons for philosophy, right? And for actually what we're doing, like why does this, all this Ioneda stuff matter before I get to the meat. So the idea, right, as I said a million times, is that we can understand an object fully if we understand all of its relationships. But of course, this is a very large space. It's in general very, very hard to know if we are even representing all of the relations that we care about to like represent the object of study enough. But the idea is that if we want to kind of approximate things and make models of things, is you have to incorporate a large enough class of these relationships that do two things. They have to both cover the space, meaning that we have to have enough of them and enough quantity of them, but they also have to differentiate if we're talking about like, for example, in the space of value or something. We want to look at all the relationships. We want to look at relationships that differentiate sort of like the material being of the things that matter or the things that we're concerned about. So for example, maybe if we're talking about the space of value, we want to make sure that we can represent maybe like the interests of all workers in this value space, and to really understand the value of all workers in this value space. So that really is about incorporating a large enough class of, right, these like inclusion relations into the value space. And the second lesson, I guess, from basically this like last slide about probing spaces, is that if we look at specific kinds of relations into or out of spaces, we can look at a space up to a certain property, like I said before. So we can look at a space, for example, up to cardinality, or we can look at a space up to its loop space. So I think this is all the stuff we've been talking about, like about sort of experiments, ultimately, in a very, very general kind of, I guess, ontological way. If you're doing some kind of experiment, and this can even be, I think, even in the case of, for example, science, but especially, for example, if we're talking about in politics, if you do some kind of experiment, it's always going to be from the lens of some probably finite set of relations. So really, to understand like the interpretation of the experiment or whatever you're doing, you need to understand the relations that you are looking at. For example, if you're looking at a space in terms of its size or in terms of some topological property or whatever. But you also need to know how these relations fit with all the other ones, and whether you're, I guess, leaving too much out.
This really looks
big
like,
picture, yeah.
Sorry, this really looks like, I mean, one thing that became more important as we went along with the discussions on our reading, for example, of Badiou, was this idea that the passage from defining a component of an object, right, to defining an atomic component is kind of like finding the coverage that is kind of correlated to some way of predicating, but it's a relevant predicate enough that the mappings that are gonna involve that cover actually extract the interesting information, right? So
yeah, exactly. So this is actually very interesting, specifically in Badiou's. Sorry, it's a bit loud outside. We got some motorcycles going by. Specifically in Badiou's atomic logic, there's a big emphasis on both of these covering and differentiating relations. So the covering is sort of can I cover the space fully and sort of cover it with all of the atoms? That's the whole discussion with the transcendental functor is about this, but also this sort of like global consistency is very important. And that is basically making sure that there isn't, that these, I guess, like these relationships aren't fighting each other to a degree. So yeah, I think there is in Badiou and it's taken into account. So it's, it's good to keep in mind. And the big picture lesson, very cliche, but context is everything. But this is another point, that this is actually something I realized as I was doing the presentation. But this is, I think, an important way to understand Badiou's focus on the size of a world. I know for a long time, I didn't understand the exact point of it, I think. Like, for example, in Being the Event, he talks about the state and the size of the state compared like to the subject or person. Not so much in Logic of Worlds, but then later when you talk about ultra filters in the section in Immanence of Truths, it comes back, the whole question of the size of the world and determining size of infinities. But I think this is really crucial here in this context, because the size of a world is not just the amount of stuff that's in it, it's also the amount of relations there are in it. And if a world is larger, if it includes more things, it's going to have more relations. And thus, if we can't, like, our tools at different scales of worlds won't always necessarily transfer. Because at one scale, you don't have access to sort of this like bigger infinity outside of it. And thus those relations that you're using to characterize whatever you're doing might not kind of fully characterize it, or might not characterize it uniquely, etc. So I think it's an important thing to keep in mind, but the cardinality of the world, this is the first place we see it. We'll see, I'm moving stuff around. We'll see cardinality pop up a little more when we get to model theory, but that's the Yoneda stuff I have now. Before I keep going, any questions?
No, yeah, I know that in Logics of Worlds, the only place that this comes in that has is very connected with what you're saying is that he says our world needs to have an infinite be of a cardinality of an inaccessible infinite. Otherwise, it cannot be logically complete, right? Yeah. Otherwise, there might be relations that are not expressible inside the world. It would only be seeable from outside, right?
I actually just maybe made a connection. I'm not sure. We'll get to it later. That might actually be related to the downward Lindstrom-Skolem theorem. We'll get to that though. Any questions on this Yoneda stuff though? Anything else before I keep going? Before we get to filters? Okay.
It's much clearer for me now.
Good. Okay. Okay, filters. So this is just a repeat. This is just a little picture just to get visualization. There's not many images in this one because there's a lot of model theoretic stuff. Maybe let me make this big. So a filter on a pose set or on any set. Really, the filters. It's on the set of subsets. It's gonna be a subset of it that has 3 properties. The first is downward directed, which is really like a closure under conjunction, which means that if I have 2 things, so for example, I have, I don't know if you can see this. If I have any of these 2 red dots over here, imagine these red dots are the filter and the black ones are everything else. So this could be a pose set, or this can be just any pose set. So there's a filter on any pose set. If we see any of the 2 red ones, their conjunction, meaning that the greatest element that is less than both of them, is always going to be in the filter. And also there's going to be it's going to have to be non-empty. It's like a trivial property. And then upward closed also. We'll see how this is connected to sort of a closure under implication. But basically, if I have anything in the filter, everything above it will also be in the filter. Okay, so
in this case, isn't this also an ultra filter?
This one, I mean, I didn't really make it very clear because you don't actually know what is the complement of what. And I don't know if everything has a complement. I just drew a pose set, an arbitrary pose set. I would have to like go through exactly. We'll get to ultra filters in a bit though.
Okay.
Okay, but in any way, like from what you just said, a filter cannot be just any part of a pose set. It needs to be a part that has some cohesion inside itself, right?
Yes. Yeah. So that's exactly. So the cohesion comes from this downward directed and this upward closed property. So I'll go into a bit more later. But this is just sort of the like traditional topological definition. But we can think of a filter as a more or less consistent set of propositions. This is the important thing. Another just notation of filters can be, we call it proper. Basically all the filters we're dealing with are proper if it's not the entire thing. And then you can also equivalently define a filter in the same way as a monotone function from the power set. So this 2 to the x, this is just the power set of x to this Sierpinski space. Oh, I guess I'm using 2 too much. This first 2 is not, this just the 2-point set. The other one is the Sierpinski space. But it's just another way of characterizing filters. But so before I get to filters sort of in logic, in topology, the reason why filters are really good is that they generalize a lot of the things that we do with sequences in topology to general spaces. So for example, I went into this last week more, or 2 weeks ago more, but many of these theorems, for example, any of these 3 down here, if you take like the spaces Hausdorff, if and only if, limits of convergent proper filters are unique. So this, if we replace the filters and the converging filters with a sequence, a convergent sequence, it actually doesn't work for arbitrary spaces. You actually need the space to already know it to be what's called second countable, which has to do with basically the basis of the topology working nicely.
What is a sequence?
Not being too ill-behaved. Oh yeah. So a sequence, it's just, I mean, a sequence is literally just any map from the natural numbers into your space.
Okay.
So it's just a sequence of points. Maybe I'll
do
drawings to make it. Let me do this. Right. So like in general, I'll just draw some pictures and make it. So if I have a space, okay, here's a space. I can imagine a sequence. It's like here, there. Okay, so it's just a list. It's just gonna be from n, right, from the natural numbers. It's gonna be just a map into there. So there's a bunch of them. There's gonna be infinitely many of them, and maybe they converge to something, maybe they don't, right? So there's a well-defined way that you can talk about convergence, and you can talk about limits. And when you study topology or analysis, generally most of the theorems will be proven using sequences and from the perspective of sequences. So sequences are kind of like this discrete way of converging to something. The reason why convergence is so important in topology is because it's all about localization and about like global consistency. But if we want to localize something, that like often it has to do with you take a sequence and it's the limit of a sequence. So you want to ask whether, so for example, you can often say a space is Hausdorff, which Hausdorff, we remember, is a space where you can tell any two distinct points apart by having them in separate open sets. So Hausdorff is going to be, if I have 2 points, they're different, I can always separate them with 2 open sets like this. There are some spaces in which I can't. For example, this I believe is called a line with 2 points or something. You can take the real line, 2 copies of it. You can identify every single point except for the origin. So you can have this weird thing, this real line that sort of has 2 origins, and every neighborhood here has both of these points inside of it. So even though these are explicitly distinct points because they're defined that way, they're defined as being different, it's basically taking the real line and just adding something to it. But that's not Hausdorff here, because these 2 points, you can never separate them. And that's just like maybe the easiest example of a non-Hausdorff space. But going back to filters versus sequences, the reason why a filter is nice is because instead of a sequence which sort of discretely converges to something, a filter converges to something basically everywhere. So maybe let's draw another one. So if I have some space, a blob, so a filter, let's imagine that it's going to be something converging to this point. A filter could be like all of the sets. So remember, a filter is a bunch of subsets rather than points. It's going to be all these subsets, right? They get smaller and smaller, and you can say how they converge around this point. For example, the simplest filter can just be the filter of all sets containing this point exactly. Okay. So the reason why, from a topological perspective, they're interesting is because it's much more general than a sequence. And you don't have any of this requirement of countability. So you can just say for our arbitrary topological spaces, you can say that it's going to be Hausdorff if and only if limits of convergent proper filters are unique. Okay, that makes sense. Another one, if you have a space X with a subset A and X, a point is in the closure. So maybe I'll draw this. So if you have X here, okay, then we have some subset A. It's gonna be A. A point X is in the closure. So the closure is going to be basically if you imagine here. Oh, let me go back to 1 second. There you go. So the closure, right? A point, for example. Sorry. There you go. A point X here. This is going to be X in this closure. So it's around the border. The closure, it can also be inside. To be in the closure, if and only if there exists a proper filter F containing A. So a filter that contains all of A that converges to X. So the filter is going to be like this. And eventually it's going to contain A. These specific theorems aren't that important. It's more the filters are pretty great. And then finally, we can say that a function is continuous if and only if for every filter on X, if it converges to a point in X, then the push forward, the pullback along this function F applied to the filter is also going to converge to f of x. So basically, if we put the filter through a function, is it still going to always converge? And that is exactly how you define a continuous function in general for arbitrary topological spaces. Oh, my computer's ready. Plug it in.
In the example you gave, you drew in the previous slide, so that converges to the lowest red point, right?
Yes. Yes. This one here. Yeah. So this one is going to converge to this point right here. Sure. Let me clear this. Okay,
yeah,
so this is filters.
Sorry,
yep,
just more comment. Yeah, I realize now that that one is not an ultra filter because you can expand it.
I think so. Yeah, I think I made it not an ultra filter on purpose. Because
right.
Filters here. I believe this point would probably not be. Okay. Anyways, we can interpret a set of propositions as a more or less consistent, a filter as a more or less consistent set of propositions. So each proposition phi, so I'll get to more detail of this later in the model theory. But the idea is that you can actually model a proposition within an ambient space as simply the set on which that proposition holds true. And we can think of this as an analog for the proposition itself, sort of within this context. Okay,
that's pretty crazy.
Yeah. So it's important that we always keep in mind that there's always a support set behind. So it's never really exactly the full proposition, but it's always the proposition in terms of some model. In general, these models will be large and will be kind of have enough flavor to be interesting. So these two axioms, this is what I mentioned before, the downward directed and upward closed axioms, if we interpret it this way, become closure under conjunction and implication. So that means that if two propositions are in the filter, then their conjunction, phi and c, will also be in the filter. That makes sense. And an implication means that if a proposition, or the support set of a proposition phi, is in the filter and it's contained in a larger set of some proposition psi, then psi is also in the filter. So the reason why this is interesting is it makes it, first of all, as we'll keep saying, a more or less consistent set of propositions. What that seems to imply is that it might be a way to sort of decide truth on the set of propositions in a way that is always going to be consistent. So there's already a hint about this model theory, adding axioms kind of stuff.
Also, just a second, like from what we just covered, we went like filters allowed us to like make really clear the connection between like a sort of inclusion relations in a topology to a sort of order relations in a post set, and now to a sort of implicative relation on a propositional logic, right?
Yes.
So you can really kind of walk around between like it's a level of generality of what we're talking about, where discussing coverages on a topology, discussing ordering of in a post set, and discussing conjunction and implication between propositions. You're using the same machinery for all of that.
Yes, exactly. So I think one of the main lessons we want to learn from this is really like the intimate connection between space and logic. And you see this in Badiou, right?
Yeah.
Where the logic of appearing comes from the physical makeup of the space. So this is kind of where, I guess, where the inspiration for why.
And I mean, I think that just to get the weird philosophical proposition from it is that spatial relations, you don't need to ask about the logical counterpart of a space if the spatial properties are equivalent to logical properties. Like, that's a totally different way of, right?
Yeah.
Like, it's not a matter of saying what is the underlying hidden logic of a space, because
the logic is there. Yeah.
The logic is in the space. Yeah, it's very distinct. Like it's a very different intuition to approach.
And it's reflected in the math as we see.
Yeah.
Okay, now let's talk about ultrafilters. So there are 3 equivalent characterizations of ultrafilters. So it can be, so if we take a filter, it's going to be an ultrafilter if and only if any one of these 3 properties hold. If it's maximal, prime, or ultra. So probably the ultra is the property that you've seen before. But the maximalness is interesting because we'll see as it comes in that there's the ultrafilter theorem about extending filters to ultrafilters. But an ultrafilter is maximal because if you really think about it, well, I guess I haven't really defined it, so I'll talk about it in a second. But the definition is if there's a proper filter that contains it, then they're going to be the same. Okay, that just means it's maximal. It means you can't have anything bigger. Prime means that if you have the disjunction of 2 propositions, you can interpret them as propositions in the filter, is going to be in it if and only if one of them is going to be in it. So it's the same thing like defining prime numbers. If if the product is in it, then either one is prime or the other, or then it divides one or it divides the other. And an ultra is the 3rd property that either for all I in the filter or in the space, in the ambient space, either it's in the ultrafilter or its negation is. Here we have to remember also negation and complementation are the same. So it's either the thing or the complement when we interpret these sets as sets of propositions. The negation of a set is just going to be its complement. But from this ultra property, it should be pretty easy to see that this is equivalent to it being maximal.
Which doesn't mean being a maximal doesn't mean that it covers everything, right? Because the proper filter.
No, it doesn't. It doesn't. Yeah. It's never going to cover everything.
Yeah, it's the largest thing. It doesn't mean it's like the largest cover, which doesn't mean it covers everything. Actually, it implies that it doesn't, right?
Yeah. So there's an explicit reason. It cannot. In fact, any filter cannot contain, if it's a proper filter, both a set and its complement. The reason why is because of the conjunction. Is that the conjunction of a set and its complement is always the empty set, by definition, because they share no elements. And in general, we say that we don't want the empty set to be in the filter because we want a proper filter. Otherwise, it's just going to be everything and it's trivial. So this is the sense in which an ultrafilter is maximal, is that if you had anything else, because if you have even one element that's complement is in it, then you automatically, by conjunction, have the empty set. And then it breaks it down, so it's uninteresting at that point. So ultrafilters have 2 varieties, as we might know. There's principal ultrafilters, which are always generated by a singleton. So this always comes in the form of, I'll maybe do a little drawing. This is working. Oh, I unplugged it, that's fine. There you go. So principal ultrafilter, I have a space. X is literally just going to be every single set that contains X, whatever it looks like. It's going to be all of these. Okay, so principal ultrafilters are also really not that interesting. But there is something, I guess, notable, is that a principal ultrafilter is exactly an analog to points of a space. So if we wanted, we could literally replace the points of a space with these principal ultrafilters, and they map one to one another. Okay, but what about non?
Sorry. That means that
go.
If you have a principal ultrafilter, meaning all coverages that include the singleton, that you can map them one to one to the points in the space.
Yes. Because okay, this is the point. A principal ultrafilter, by definition, is an ultrafilter generated by a single point. You can have, for each point in the space, you have one such ultrafilter. That's the bijection. So it's simple, but it suggests that we can look at the space through its ultrafilters, right? So if we look at a space through its ultrafilters, we already have all the points. So we already recovered everything, but we get something more, maybe, potentially. We get maybe these non-principal ultrafilters, which are strange. But a non-principal ultrafilter can be one that just is not defined by a single point. But when you start to think about it, if it's not generated by a single point, in fact, it's intersection. So if we take an ultrafilter, imagine if we have this here, it's intersection. So let's say this is the points of the ultrafilter. This is supposed to go down. Oh, whoops, that's fine. Okay, so this is a kind of weird looking one. But imagine we have an infinite ultrafilter. Okay, so this is infinitely many things. This is going to be, I guess I'll just draw over. This will be the top element. Okay. So if it's a principal ultrafilter, if we intersect all of these, what's going to happen is it's going to intersect at one point, and then basically everything is going to converge to this one point. Okay, that's actually not what happens in a non-principal ultrafilter. Because if we remember about this conjunction,
they converge, they have intersection on one point when they're principal. Because they all,
when they're principal,
Because then they all have the singleton in common.
Yeah, if we remember the conjunction property, what does it say? Let's just go back to it real quick. Oh, I can't. There you go. The conjunction property is here. It says that if we have two things in the filter, then there's going to be another one which is in the filter, which is their conjunction, or this should be equal to the conjunction. But the important point is that this conjunction is, am I on the next page? Yeah, the conjunction is only finite. So it does not imply, because it's only for pairwise things. So it's saying if I have this point and I have this point, let me go back to draw. If I have these 2 points, then I must have their conjunction. Okay, that's fine. But that's not true for the conjunction of an infinite set. So if you imagine this is infinite, it doesn't have to all converge to a single point. Only finite subsets of it do. Meaning, and this is exactly what a non-principal ultrafilter is. It's very strange. It's going to be a top, but then it's not going to converge. But it's going to be this weird sort of decision of infinite quantities. So I think one good way to think
like
about
locally, there are conjunctions for any two things. They have a conjunction
for any finite. In fact, for any finite.
But if you take them and as for the conjunction of an infinite set of things, you won't find like this common thing.
Yeah. You don't. Well, you can, but you don't have to. Is the thing. So the existence of non-principal ultrafilters is really like a deep and interesting question. And
totally
ultimately,
crazy.
It is totally crazy. In certain contexts, they do always exist, and we'll see why and we'll see how. But I think a good way to think about them is, well, a principal ultrafilter, right? It's something, it's going to always converge to a single point. as opposed to a filter that can converge to a set. An ultra filter is always going to converge to a principal ultra filter is always going to converge to a point. A non-principal one, we can think of it as sort of converging at some sort of like infinite singularity. So this is really where it becomes interesting, and where we see that eventually it's used. Non-principal ultra filters are a way that you can actually bring an infinity or some infinite quantity into the situation in a way that really disturbs the whole thing. It really can change it, and it really can like add an axiom, for example.
But for example, if you turn this now to the discussion in terms of propositions, right?
Yeah.
The principal ultra filter is a way of covering, let's say, the reference space of your propositions in such a way that the ways you're predicating on it ultimately have some bottom predicate that separates something singular.
Yes. So it's always generated by, it's like a truth generated by a singularity. Yeah.
Right. Whereas with the non-principal ultra filter, even though for finite subsets of that space, you can find a predicate for it. When you ask about the common property of all of it, right? It doesn't really, you don't really necessarily have a, right? It's in predicative.
Yeah, exactly. So this is the way in which it's sort of like this like infinite singularity. And it's never going to reduce simply to a point of the space. So that's really where they become interesting, because we're sort of inspired by principal ultrafilters being an analog for the point of the space. A non-principal ultrafilter is sort of this like infinite point that you cannot reach from the space, but you can maybe presume its existence and maybe construct a model in which it is literally there.
I mean,
I have a question here.
Yeah, Dennis.
Yeah.
Just so we're saying that the fact that they don't share a singleton doesn't mean that they don't share anything, right? They do share something. It's just that thing is not a single element.
No. So actually, if you intersect everything of a non-principal ultrafilter, it's always going to be empty. So if you take, if I have this non-principal ultrafilter, if I take this non-principal ultrafilter here, okay, we're just going to imagine it's infinite. If I have this big thing, if I intersect over all of these, it sort of covers a very large space. If we think about like horizontally almost, right? It's going to hit many, many, many infinite sets. But if I take all of these things, right, and if I intersect them all, I'm always going to get the empty set.
I see. But don't you have the same situation with finite post sets in which every branch like terminates, like every branch is separate and terminates at the null set?
What do you mean?
Like, let me see if I can draw. Okay, like because you're showing an infinite case, right? But isn't this also have the same property? Just something really simple like this, and this is the null. Like, can we say that?
Yeah, but that's, I mean, that's not an ultra filter though.
Oh, right. It's not a filter because
it won't be. Well, I mean, the whole thing could be like a non-proper filter, but it can't be an ultra filter because it's.
Okay.
I mean, a non-proper filter is just the whole thing. I don't know why I said it like that.
Yeah.
But this is, I think this is where you get the craziness of like why it's so informative, because you're covering the space. It's not the space itself. You don't want the trivial statement of what everything is in common is nothing. Like, that's trivial, of course. Like, there's so much stuff. The intersection of all of it is gonna be nothing. But the fact that you have structure built on top of it, you're actually covering it all with propositions that are structured upwards and downwards, and still the intersection of your propositions is only nothing.
Yeah.
That's kind of capturing that property that trivially is actually totally useless, right?
Yeah, it means they can't, none of them can be sort of like broken down into any single point. It's always this strange infinite quantity. In fact, non-principal ultrafilters literally have to be infinite. It's impossible to have in a finite space. Non-principal ultrafilters don't exist ever.
Okay. Thanks. Yeah, that's good.
Yeah.
Just to give a side note on this that I think is important is that Badiou makes the distinction between he says, if you look at the way that left usually organizes, the only way it can dislodge he suggested social organization under capitalism. It has all this infinite differentiation, but ultimately what they all have in common is money. So everything intersects at the fact that you can get at everything from money, right?
Yes.
And he says, well, the left has managed to dislodge this, but always by choosing a new singleton. So for example, having a proper name of a leader, even though everything that happens is still highly differentiable and highly structured, ultimately you need that sort of common point at the bottom to guarantee that there is some cohesiveness, right?
Yeah.
That what we haven't managed to do is to come up with a structured recovering of a space that doesn't require the common to be a positive underlying element, right?
Yeah. Along these lines, right? An ultrafilter, when we talk about it as these more or less consistent sets, an ultrafilter is going to be a maximally consistent set. So what that really means is that, well, first of all, is that basically it obeys the law of the excluded middle. That is just literally this ultra property. But even more so, it means that an ultrafilter, it's a way to decide truth globally and consistently. It decides everything in your post set or in your set that the filter's over, but it decides it consistently. Right, so then this is the point I was talking about. Principal ultrafilters, not really interesting. They always go down to a singularity, but a non-principal ultrafilter, they give this sort of infinite singularity. So it's going to so this is why it's crazy when you look at it from this maximally consistent set. This non-principal ultrafilter is it will decide every single proposition in the set as either true or false, but at the same time will not ever be reduced to any finite being, or even any singleton, or even a finite set. So we'll see coming up that non-principal ultrafilters are really important for forcing in model theory set theory, which hopefully we can get a little bit about. Yeah.
You mentioned is different from the reversal in the transcendental, right? It's because it's the complement.
Wait, can you repeat that? What when the transcendental?
You mentioned the negation of a statement in the ultrafilter decides. It's different from the reversal, the negation in Badiou's transcendental.
Yeah, because for Badiou, when he's talking about these post sets, right? He talks about, he defines negation in this space, which has this this structure and so on and so forth, right? By saying that the negation of P is the envelope of everything whose conjunction with P is nil. Right.
The envelope of everything whose conjunction. I think that.
Yeah, but the point with.
Oh yeah. So that's exactly the complement.
No, yeah, but the complement.
So
But here, this is intuitionistic, meaning that the reverse of the reverse is not necessarily P, depending on the structure.
Yeah, it doesn't have to be. Yeah. So
right.
It doesn't have to be.
But for the ultrafilter, it is classical because.
Yes.
So it's a stronger condition than the negation. It's a classical negation.
The idea of the ultrafilter is it forces the entire set to obey the law of the excluded middle, essentially. So it forces it to be classical.
Yeah.
But that's really where I think where the interesting part of forcing is. It's deciding truth in a global way. But yeah, of course,
And it's so it's so weird that like from a layman's perspective, it seems like mathematics became more interesting because it doesn't require such classical logic. But actually, so many contemporary results are interesting by making use of classical negation to be able to move from, like, for example, the structure to something that concerns the set as a whole. You won't be able to talk about the set of a whole directly, only by defining that you are dealing with the complement of the set.
I think it's useful also, the whole thing of forcing either the negation or the thing to be true gives a tool to work sort of within even like a I can't say the word, intuitionistic logic. But yeah, in general, the complement of the complement doesn't have to be the same. In like a Boolean algebra, that's true, but that does not have to be in general. And I believe for ultrafilters, it will sort of force it to be that way, but in such in general, you don't. Okay, so this is, let's add a little nice Banach-Tarski picture on the bottom. But the ultrafilter theorem is sort of the main important result about ultrafilters. You might want to call it an axiom instead, depending on, I guess, what system you're working in. But the statement is very simple. It's every proper filter can be extended to an ultrafilter. Using this, if you simply take an infinite set, an infinite filter, then you can, as long as it doesn't intersect, all the things intersect at the empty set, you can actually extend it to a full ultrafilter. So it turns out this ultrafilter theorem or axiom is actually, it's a weaker version of the axiom of choice. So the axiom of choice, of course, can prove it, but it can't prove the axiom of choice. But you can actually use it to prove a few classical results. For example, the Banach-Tarski paradox, which maybe some of you know. This is a picture of it, just to kind of quickly go over it. The idea is you basically can take a sphere, you can slice it up in a strange infinite way, and then you can reassemble it in such a way that you get exactly two spheres of the original size. So this is something that, like, for mathematicians, for a while they called it the paradox. Eventually, basically most have come to terms with it basically by saying it doesn't really matter if this is like a quote unquote realistic scenario, because really to do this, you have to cut it in this like infinitely fine way. So it's basically a way to show that when things are infinite, they act very strangely and intuitively. For example, you can sort of create something out of nothing because you just take the sphere, you cut it into pieces, you rearrange it, and then you get two of them. Seems to break some laws of physics, but it's okay as long as you have infinities. Also, the existence, the ultrafilter theorem guarantees the existence of non-trivial ultraproducts, which we will get to, which are used in forcing. Losch's theorem, we'll talk about at the very end. And also, you can use it to prove the compactness theorem for first order logic, which we also will get to. That's a bit about the ultrafilter theorem. I'm just going to take a little quick detour because we've talked about ultrafilters. I just want to mention another connection, which is a very strong connection between, between topology and logic. And it's really a set of theorems called stone dualities or stone type dualities. It's based on the original Stone's representation theorem, which is an isomorphism between Boolean algebras, which, as we know, are models of classical logic, and the set of ultrafilters containing a point generating a basis for this thing called the stone space. A stone space is just going to be this right here. It's going to be any compact. So compact, remember, is basically everything that converges in a compact space will converge into space. That's the important property of compactness. So any compact, totally disconnected Hausdorff space. So really the thing that's striking about this, might seem a little technical, is that if I have a Boolean algebra, which probably from BEDU maybe know a bit about Boolean algebras, Heyting algebras feature quite strongly, which is a more general version of Boolean algebras. But Boolean algebras will model a classical logic in the sense that they can be all of the sets of propositions with law of the exclusive middle and conjunctions and implications and everything. But it gives an isomorphism between if you take a Boolean algebra and then you take ultra filters on the Boolean algebra, you actually get this thing called the Stone space, which is any compact, totally disconnected Hausdorff space. So if you want to draw a picture, you can actually draw a picture of a Stone space. It's going to look right. So it's compact, meaning everything is gonna converge to it if it's going somewhere. Totally disconnected means it's just a bunch of points Hausdorff. So basically, it's just a Stone space is just a bunch of points floating in space. There can be infinitely many of them, but as long as you can differentiate any 2 points, and they are totally disconnected, meaning that you won't ever get this thing where you get like points that get infinitely close to one another. Mm-hmm. But the interesting thing is that it seems like there's no reason why this Boolean algebra, which is a model for logic and really comes from George Boole studying basically like the early model theory, and these specific types of topological spaces. But it turns out that they're dual to one another. One is sort of the opposite of the other. The connection is because it really gives a connection between this whole logic and topology. You can generalize this as well. There's a bunch of other Stone dualities in NLab they give. So this is a difference that I won't say I completely understand, but they claim that the Stone type dualities are really a duality between space and quantity, where space is represented by presheaves, and then quantity is co-presheaves. Although, as I said, I don't really follow that argument. But they do definitely give a connection between topology and logic. And then also generally, the one that we have maybe seen is this duality between locales and frames.
Yeah.
So a frame, this is just a complete Heyting algebra. A locale is basically a topological space, although it doesn't have to be based on a physical set. It can just be the space by itself, just the open sets. So it doesn't actually have to have points in it. It doesn't actually necessarily have to have enough points. It's just a small, I guess, detour.
And the ultra filters enter in the Stone type duality because if you can come up with the filtering of the Boolean algebra has the structure of this compact, totally disconnected Hausdorff.
Yes.
Okay. Mm-hmm. And we're talking about
exactly.
We're talking about principal ultra filter.
This will be, I mean, on a Boolean algebra, unless it's really big, and I don't know if you can have non-principal ultra filters in Boolean algebras. I suppose you could. I don't know if Boolean algebras are normally sort of like uncountably infinite. But yeah, I have to think about that.
Yeah, but okay, but the ultra filter part I think is clear for me because the law of excluded middle already holds in Boolean algebra. So the idea that the either something is in the ultra filter or it's in the complement is actually kind of building to the algebra itself.
Yeah. And also if we have any Stone space, conversely, we have a Stone space and we just take the Clopin sets. So Clopin is going to be sets that are both closed and open. This is exactly going to be the Boolean algebra that corresponds to the Stone space. Okay. So it's a topological relation. These dualities, I believe, are still something that sort of in the most general framework aren't completely understood, and it's still kind of an active field of research. in terms of like, to what degree do these types of dualities extend, or if there's like a single unifying connection. I believe Dennis, you would know this Joyal paper, that topology one. I believe this whole duality between topos and logos, which we won't get into, but I think it has to do with this duality in a more general, kind of higher categorical sense.
Yeah, I added another text that I thought was very useful or helpful
nice.
to the chat.
Nice. Yeah. Okay. I also have a pretty good paper that talks about like model theoretic forcing, kind of from a more philosophical perspective, and interested specifically in like sets of propositions. And it's much more readable than most math texts are. So I'll send that one as well, if you guys want to see it.
Yeah. So can we basically say that spaces are a model? Like, I mean, there's a certain sort of structures that you can add to spaces to make them into models of.
Yeah, we'll get to models. So models is basically just a space with an interpretation function.
Cool.
That gives you a way to interpret. That gives you a way to interpret formulas. I believe, is that the next? Oh, okay. First, we're going to talk about just first-order languages and signatures. So we know a first-order language in general is going to be the syntax we use to write down logic. So it's going to have logical symbols, which are things like there exists, for all, the conjunction, implication, parentheses, even punctuation, all of that kind of stuff, including also variables. And then there's going to be non-logical symbols. These non-logical symbols are kind of extra structure, and they are ultimately what kind of like the stuff of the language is comprised of. So the signature is going to be just all of these non-logical symbols. So for example, if we just want to look for a group, which I don't know how many of you are familiar with groups or fields or anything like that. A group is just something that has one relation, basically like an addition. It has an identity element, and then you can always take an inverse. So the signature of a group is just going to be the constant for the identity, 0. You can imagine a group as being, for example, the integers with addition. Then there's also a plus, and then there's going to be the minus, which is the inverse, gives you a negative number or the inverse of a element of the group. Also a field, which is more general, will have 2 identity elements, one for multiplication, one for addition. You can divide and everything. We'll have this signature, which makes sense. And then if we want to talk about set theory, ZFC has a signature, which is just the empty set and the inclusion relation. Okay, so now with that, we can define what a model is. So a model it's going to be a pair over a language. So there's a language fixed in the background. We're just going to call it L. So remember, a language also has the signature. It's going to be an ordered pair. It's going to be this D set, which is just a non-empty domain. So it's whatever set the model is based on. And then this interpretation function from the language, really from non-variable constants and predicates and things like that, is going to be an interpretation function on constants and predicates in the language. So for a constant, the interpretation is just going to be some element in the set. So if I have some constant, for example, the empty set is my constant. If you want to look at what the interpretation of the empty set in ZSC is just going to literally be the empty set in ZFC. That's kind of simple. If we have a predicate, it's going to be pi taking n arguments, so pi from alpha 1 to alpha n. The interpretation of this is going to be in the product of this n times. So it's basically going to pick out the lists of n elements that make this predicate true. Okay, so right now we only have a model defining an interpretation function on constants and predicates, nothing else. Then there's a variable assignment which is where if we take a variable of the language and we give it an explicit thing. This is if we want to have a free variable in the formula, for example, if we want to say there exists x such that p of x, you need a notion of how to like plug in a variable. So that's what this variable assignment is. And then this is, I'm taking this notation from the paper that I mentioned. Gabriel, I can send it also. I think you were gone when I mentioned this. It's a good one.
Is the one Danny sent on the chat on the?
No, it's a different one. It's on model theory and sort of in the context of philosophy, and it's more approachable than most. It's
cool.
probably the most approachable model theory thing I've seen. It's pretty good. And this denotation, which is also used there, is just going to be basically putting the variable assignments and the interpretation together. So if it's a variable, you just put the variable assignment in. It's always relative to variable assignments. And if it's, we got a fire truck going by. Might get loud for a second. Okay, left. And then if alpha is a constant, then you just plug it into the interpretation function and see what it comes out. And this last little piece of notation, if I have a variable assignment A here, this little symbol saying X triangle O is just going to say, if I have a variable assignment, I'm going to replace X with O. Okay, it's just changing
one stupid question. Like here, it's here it's L. It's not the domain of the model. It's the domain of the language.
No, L is the language itself.
Okay, so.
Oh, yeah. Sorry. Yeah, that should be. Yeah, my bad. It actually should be M. One sec. That is my bad. I can't see this now. Whatever. I'll just fix it later. Yeah, that's just typo. Okay, so this is the basic definition of the model.
One question. So for quantification, where does that come into play?
We will talk about it right now, actually, in the next slide. Yeah. So as we saw, the whole like interpretation function is basically just giving you elements of things in your set. So it's not really doing a whole lot. So if you actually want to do logic on the model, you need to do more things. So the truth of formulae, and it's written like this, it's always going to be with respect to a variable assignment. So I'm going to say I have these variables and these are assigned to certain sets. It's defined recursively. So this right here, this is saying I have a model M with a variable assignment A that models phi. That's what we say. We say that the model models this proposition or set of propositions. And basically what that means is that those set of propositions are true for something in it. So for example, if we want to say that if it models a predicate, it's going to be if and only if each one of these individual, what they call these denotations, which is the interpretations of variables and constants, if and only if, this is going to be in the interpretation of the predicate. Because remember, we actually can interpret predicates. Equality between things, between two constants or variables, would be if and only if. Their denotation is the same also. A complement right here, it's going to model the complement of a thing if and only if it does not model phi. Okay, that's fair, makes sense. Conjunction, the usual thing, and then here existential quantification. If and only if there's some object in the domain such that if I take this variable assignment and if I replace it with O and it's in phi into this predicate. Okay, does that make sense? This is a bit confusing because it seems to be kind of defining truth by itself, but the important thing is that it's a sort of a local truth within a model. And a model, what we want to keep in mind about what a model is it's a connection between syntax and semantics. So it's saying if I have a syntax, how and what are the ways in which I can determine how to determine truth values of different sentences in that syntax. And it gives a general structure for how to do this. So there's a lot of notation. Hopefully it's not too much. But there are two very important theorems for first order models that actually give you that they are basically the best models of logic in a way. We'll see what that means in a few. But the first one is compactness for first order models. So what this says is that if I have a set of first order sentences, okay, so if I have a set of sentences, I want to see if it has a model. So is there some model for which the sentences are modeled by it or true on it, in the sense of the last slide, if and only if every finite subset of the sentences, right, has a model. Okay, so this is saying if I have an infinite list of sentences, if I want to determine if they're all true, I can test each finite subset of them. So this theorem is actually a consequence of Teknov's theorem, which I believe I talked about a bit last time, which says that the product of compact spaces is compact. You can actually use ultrafilters to prove this, if you're curious. But it's a consequence of it applied to stone spaces. So remember, the stone spaces were the sort of topological analog to Boolean algebras. So it implies that every theory has an arbitrary large model. Because basically we can keep taking larger and larger sets of sentences. And we can always determine that it has a model if and only if we can figure out if a finite subset of them does. And we'll get to a more even stronger point than the second one. But a third thing I want to mention, maybe not spend too long on it. This is actually one of the ways that you can use, that you can construct is the non-standard reals. To do some non-standard analysis, if that's what you're interested in. Just because Gabriel mentioned this a little bit, so I thought.
Yeah, the Robinson thing.
Yeah, just throw it in as a little thing. There's other ways to do it using ultra products, but this is, I think, an easier way to understand it. So we can take the real numbers, we can adjoin an element, we're going to call it epsilon, because it can be small. And we can also give the axioms, epsilon is greater than 0, okay, that's one axiom, and epsilon is less than 1 over n for all n and n. Okay, well, that's infinitely many axioms, okay? So we have infinity plus 1 axioms, right? Yeah. So we can actually use this. We can say that if and only if every finite subset of it does. Well, the interesting thing is that since it's every finite subset, we can just take a finite subset of these natural numbers, fix epsilon to be greater than 0, pick some numbers such that for this finite set of natural numbers, it's always going to be less than it. Since these are the axioms we're adding, and since the real numbers are sort of consistent within themselves, I'm leaving details out, obviously. I just wanted to add it. You can actually use the compactness theorem to show that there is actually a model of the real numbers that has this weird element epsilon as well, which is both greater than 0 and smaller than every single fraction 1 over n. So it's always going to be smaller than any real quantity greater than 0, but it's also going to be greater than 0. So it's in between 0 and everything else. But we can actually use this compactness theorem pretty quickly shows that there exists a model of this non-standard reals. And you can do a similar thing to add an infinite quantity, basically saying it's greater than n for all n. And it's the same kind of argument. I thought that'd be a little interesting side note. But the second one is the downward Lowenheim-Skolem theorem. This is the really interesting one. So if we say for any infinite model, so if we have an infinite model over a first order language with signature sigma, so this is the non-logical symbols, and then any infinite cardinal number, which is greater than the amount of symbols in the signature. there's a basically meaning that we need at least, we're going to need at least kappa, at least the sigma number of cardinality of this model for it to work. You can't have a model with a smaller cardinality than its signatures. So if we have this, we have any infinite cardinal number greater than the signature, the size of the signature, there's going to be a model n, a different model, over the same signature in the same language, with cardinality k such that one of these two. So if, it depends on the size of this k number, if it's less than the size of your original model, then this model that we're guaranteed to have is going to be I'm moving stuff around, is an elementary submodel of M. So this is a way we can find a submodel completely characterized by the size of this number. And if it's greater than N, which is something that exists, is going to be an extension of M. So this is crazy because it's
that's really absurd.
Yeah, it says that basically any first order infinite model has a model has an extension model that is as large as you want. So what it means is that first order theories cannot control the size of their infinities, no matter what. You can't limit the size of the infinity of a model of a first order theory. It's always going to have, it says, look, for any cardinal number grid. So it's a big theorem. The compactness is pretty strong, but this is arguably more profound. The interesting thing, right, that if we look at, for example, a second order theory, you actually, because of this, you actually have to, if you have any second order theory, you actually have to differentiate between certain infinite cardinalities, which you don't necessarily want to do a priori. Maybe there's a reason to do it, but second order theory, which second order, if we remember, just means that the propositions can take propositions as arguments as well. But a second order theory or second order model is always going to have to already decide on the size of certain infinities.
Okay, but just to make sure I follow. So yeah. Given, if I have a model that is infinite.
Infinite model.
Yeah, for the first order language, blah, blah. That means that I can always find a model that if the cardinality is larger than the original one, it is an extension of it. And if the cardinality is smaller than one, it is a submodel of it.
Yes. So it means you can always grow the model, or you can always shrink the model.
And the connection that is preserved is that if everything that is true in the original model remains true in that extension or in the submodel.
In the submodel, it will hold. In the extension, it won't necessarily, I believe, because a submodel will just be a smaller, basically a smaller version of the model. It won't necessarily cover everything, but it will agree on everything. But when you add something, when you make an extension of a model, it could mess things up, as we know, for example, by extending maybe ZFC to include the continuum hypothesis.
Yeah, that's what I wanted to know. Like, how does this result is just, I see why you phrased it the way you did. Like, just saying that, look, if you have an infinite model, you can't prevent that by adding some crazy new axiom, you won't get something larger with some weird new property that includes what you had before. So you cannot restrict that beforehand. Right? Like when you say that, I'm trying to understand, like, how do you connect the Lowenheim-Skolling theorem? Like, what are you obliged to admit when you say you cannot control the cardinality? It's not simply saying, there is some other model with a larger size. It's you are now required to admit that there will be some sort of recasting of the previous model that you cannot prevent that there is a recasting of the previous model on a larger model that will have what relation to the original one? Like when you call it an elementary extension, you said true. It doesn't preserve that everything that was true in the original is true in the new one, because, for example,
it'll have an inclusion. So an extension will have the original model as a sub model of the bigger one. Yeah.
So it will be included in the new one, but that doesn't
It'll be included in the new one.
Okay. No, that.
But yes, basically you can always, it doesn't matter how many axioms you add, you can always decide more about sizes of infinities in the first order language, the first order model. You'll never finish with infinities, basically. The second order model, you're sometimes forced to make a decision about infinities. I don't know the exact details about why that is, but there it is. Okay, so these two theorems come together in this famous one called Lindström's theorem, which says that first order logic is the maximal logic satisfying both the countable compactness theorem and the downward Lowenheim-Skolem theorem. Of course, as I said, it implies that higher order logics must differentiate between different cardinalities. There will be some sentence, right? If we have a higher order model, there would be some sentence that has a model of some infinite cardinality, but not necessarily all of them. But the thing about this, because we always have this Lowenheim-Skolem property, where there can always be more infinities, that any proper extension of a first order logic is always going to detect something non-trivial. It's always going to decide something about these infinities that was not always decided before. But if we have a second order model, that can sometimes already be done, already sort of be decided beforehand.
When we say higher order logics, are we saying that we're dealing with relations of elements instead of elements? Like what exactly makes a logic
so a first order logic is a logic where the propositions just take elements of your base set. Okay. But the higher, for example, second order logic can determine the truth value, can plug in the proposition to a proposition. So you can have a proposition of propositions.
Right. So you're quantifying over propositions.
So you can quantify over propositions rather than just over elements.
Right. Okay.
Yeah.
So
one thing that
sorry. Yeah, so just to go before, like you can see why the Lowenheim thing is so important in being an event, because if you can characterize a situation, true first order logic as an infinite, if it is infinite and characterizable by first order logic, then you need to allow, like you have to deal with the fact that there's something in excess to that model. Like,
yeah, there will always be something in excess.
Yeah, you might not be able to do anything about it, but that possibility is built into it, right? I mean, it's similar to the critique people make of logics of worlds and things we discussed, like why restrict your mathematical formalism, right? But it's the sort of restriction that is interesting because it kind of implies that something else can still be done, right? It's actually richer to be able to characterize it in a simpler way, because it allows you to also state that something else is also possible, rather than fully characterize it like a...
Yeah, exactly. So the importance of this Lindström's theorem is because, well, first of all, it's saying it's a maximal logic satisfying both of these. So I can't sort of get any bigger. If I go to a larger logic, like a second order logic, then I will lose these properties. But the countable compactness, right, that is actually how you can determine concretely whether there's a model of something in general, because in general, these models will be very large and infinite, or the sets of propositions will be large and infinite. And you want to determine whether there's a model of them. But in general, you can't necessarily do this in higher order logics. So first order logic is sort of the compactness theorem makes it sort of much more tangible that you can actually work with it by proving things on any finite subset of it, where showing something on an entire infinite subset could be very difficult. And of course, this Lowenheim-Skolem theorem about always there being some kind of excess. So it's not always, yeah, as Gabriel said, it's not always just more interesting to look at things that I guess are like in greater generality or larger, because sometimes you can lose something also, and so as is in this case.
So does that mean that the because of the infinite extensibility of first order, you can express anything in first order that you could in higher order logics, or is that a different thing then?
No, not necessarily. Because I mean, higher order logic, for example, can express certain things that first order logics cannot. For example, they can express, I think I saw this example earlier, they can express the idea that anything that is colored, right, rather than something that doesn't have a color, has a specific color, right? If you want to say like this red thing is colored, if you want to actually talk about these properties, quantified over other properties, you need like something like a second order or higher order logic.
Yeah, I think it's a weird trade-off between, you mentioned, John, expressibility, right? It's a strange trade-off between wanting a formalism that expresses everything at once and wanting a formalism that expresses, let's say, the limits of expression. Like, it's interesting to have a weaker formalism because then you can also say something about the limits of what can be said in that space. Whereas if you have you formalize something as everything is expressible within this theory. This is why, like, Badiou's ontology is a theory of situations and not a theory of ontology. It's not about saying what is expressible in general. It's about saying what is expressible in a situation. This way, it's weaker, but it's weaker but in a non-trivial way. Like, you can talk about increasing expressivity. That becomes a thing. Whereas you could have this sort of global ontology where everything is always expressible, but then there's nowhere to go. And I mean, nothing, you never get to express anything specific about anything, right? It's always too much.
Yeah, and the whole thing about expressibility from model theory too, like, if we look about in general mathematics and like mathematical structures, if we're thinking about, for example, like a group or a ring, if we want to add an element to it in general, it's going to make the space larger and more expressive, and it can sort of do more stuff. And generally, the original model will be just simply included in the larger extension. The thing is, when we do model theory, where the things we add are like an axiom, what happens is that sometimes things won't like work well together, and you can get basically like things canceling out and not being exactly consistent to how they were before, even though it is an extension. So I guess I actually have to correct something I said before, that an extension doesn't always necessarily have an exact inclusion in a model. Okay. It sometimes will, but it doesn't have to be, just because of when we add axioms, it can do very, very, very strange things. Yeah. Like, for example, the continuum hypothesis actually makes the set, or not the set, I guess the class of sets smaller than it was before in a sense. Because it's deciding, it's going to say, okay, I'm going to have the natural numbers, I'm going to have the reals right after it.
One question, okay,
yeah.
Perhaps, okay, you're going to go there anyway. I was going to ask if, I mean, the way we talked about interpretations seems to have a connection with, like, filters.
Yes, that's exactly where I'm going right now. Okay.
I'll just be the Robin to your Batman, like.
Yeah, the
hey, Asha, are there connections between?
Okay, so if we actually want to look at models and filters, we want to look at spaces of models. So a space of a model is just going to be a set of models of the same language. No other restrictions, just a bunch of models. So we're going to say that a J proposition, okay, so it's going to be a proposition with respect to the space of models J, is just going to be any subset of J. And then, of course, we're going to have the necessary proposition. It's like truth is going to be J itself, the whole thing. And then the impossible proposition is going to be the empty set. Okay, that's familiar. And then J. Okay, yeah. So if we have if a subset P of J, so it's a subset of models, are a bunch of models that make some sentence phi true, then we say that phi is gonna, oh, this should be a J. Phi is gonna J, I don't know why I put in LaTeX, is gonna J express the set P. And we write it like this. So this is a way to actually kind of formally make the difference between the actual proposition and sort of the set that the proposition is representing. So here, phi is some sentence. And then when we put these kind of brackets, sub J is just going to be the set on which phi is true of these models, the set of models on which they model phi. Mm-hmm. And then falsity is, of course, the empty set, impossible proposition. Truth is going to be the whole thing. And then you get all these normal conjunctions by taking intersections. You can do disjunctions with unions. This also should be J. I decided I wanted to, I don't see it right now, so it's fine. I'll just leave this. We just take complement to do complementation. This last one is interesting. In a model, we say that the set of a proposition phi, subset of a proposition C, if only if set implication is the entire thing. So what this is saying is basically the set of the implication is going to be truth. It's going to be the necessary proposition if and only if we have one is contained in the other. So this is exactly what I was mentioning before about how subset inclusion in a space of models actually becomes implication, logical implication.
Are we in Olivia
to know?
Sorry, yeah. Are we in Olivia Caramello's territory? Because
yeah, so this is just general model theory, and but yeah, why?
So my point is that, I mean,
she generally works as
you seem to be defining, let's say, yeah, okay, it's like in a restricted Caramello theory, because you're defining propositions not on the models, but on, let's say, the proposition that is true for a bunch of models at the same time.
Mm-hmm.
So we're looking for, let's say,
I guess so, maybe. It's like, not from her. This predates her, though. But
sure. And I mean, it's more restricted to model theory, right?
Mm-hmm. But I mean, what she works in is almost exactly on stuff, but she's more talking about this is bridge everything. Mm-hmm. Okay, space of models where we have propositions. The important thing to note is that while these conjunction and disjunction, they're still relative to the set, but I almost like strongly they're defined more within themselves. But the actual complement implication are almost completely dependent on the ambient space, which is just an important thing to note. So the ambient space is very important, and we have to make sure to choose like a large enough space of models so that the and negation work in the way that we want. Okay, so now we can take a filter on the space of models. Okay, so we have a way of models being, or propositions being subsets of one another in a model. So filter, as we know from before, it's gonna be a choice of consistent propositions. And it makes sense now in our space of models. Filters are the propositional analogs of theories. So what this means is that if we have a, if this set, which is going to be the set of models where when I put in X variable assignment and F is applied in the filter over J, then when we say that G, this element here, G is F in the sense that it respects, or it makes this proposition true. We say that G F satisfies, or F, maybe I shouldn't have chosen F for filter as well. But if we choose a set of J propositions by which to extend the model, for example, we can take base propositions, which are like the axioms, okay? Whatever they want to be. But now that we have a notion of proposition sets, we can like filterize those propositions, right? So we can take those like axiom propositions, we can make them upwards closed, so everything that they imply is also true, which makes sense. And also the conjunction, finite conjunctions of these axioms are also going to be true. So this is a filter in general, but not necessarily an ultrafilter. This is where the ultrafilter theorem comes in and why it's important, this weak version of choice. Because to build an ultrafilter, which sort of like decides these axioms, you pick whatever you want, and then you extend them to an ultrafilter using this theorem, which is basically, it's a simpler version of doing the axiom of choice, of choosing infinitely many things. Mm-hmm. And then if we take direct products of models satisfying each of the J propositions. Okay, so we're gonna take a bunch of models. These are all the models that satisfy whatever our set of axioms or propositions that we care about are, okay? These are the MIs. Each MI is going to be some model that satisfies some of these propositions. So first, if we take this product over it, okay? The direct product is just like the same normal product you're used to with the whole product of these M's, just call M1, M2, and 2 is just be another place. It's a limit. So it's a thing that can see both of them, right? Such that if there's another place that can see both of this thing is unique, okay? So we're taking that normal limit over this whole big set of propositions. The quotient. So quotient is a way to identify points of the space and to like glue them together. So what we're going to do, we're going to define it by a relation where A and B are both in this product, okay, of the MIs. Okay, so some elements of the product, we're going to say they're equivalent if and only if list of indices, okay, of I. So the important thing is it's over an index set. All these models, I deleted everything. Oops. All these models are over an index set. So, and the filter itself is actually over in the sense that A is going to be equivalent to B if and only if the set of I and I is in the filter. So what this is doing is it's defining a quotient, okay? So it's finding a way elements of this product are equivalent. So then if their equality in their equality, sorry, the list of indices where they have equality is in the filter. So if the filter basically identifies these two, if they're both equal according to the filter. Does that make sense? So we're using an ultrafilter to find this quotient, which is going to identify a bunch of things of a product of a model. So the idea is that, right, this, remember, is a bunch of models. This is many, many, many models. So I have a bunch of different models that might not interact or whatever. I'm taking a product over all of them. Okay, I have this big product over the MI, and then I'm going to quotient out by this relation, by the filter. That any two elements are going to be equal if their indices, because remember, this is a product, meaning that for each A, for example, there's going to be an A1, A2, A3, etc. right? Because it's going to be it's going to be elements from a bunch of models taken. So they're equivalent if wherever they agree is in the filter. So the filter, the ultra filter, decides, and I take a product of a bunch of these models, basically how to glue them back together so that they're globally consistent. And that's the important thing, is that they glue everything over this product to make something which is just going to be a single model on its own. It's going to be one unified, consistent model that is going to have all of these propositions, these J propositions that we set, these like axioms. It's going to satisfy them all if it's done over the filter. In fact, it's going to have to be a non-principal ultra filter in general to do anything interesting. That's the idea. This is
crazy.
A lot. Yeah,
that's crazy.
Yeah, this is crazy.
Totally
it's like
hopefully that kind of makes
gluing
sense.
together.
I have the final theorem next. Yes.
But I have two questions here. One is a comment. I think Gödel's completeness theorem has some relevance here, because isn't that theorem saying that a proposition? Yeah, the reason we need this product over all models is because a proposition is true only when it's provable in all models, right, or something like that.
Yeah, something like that.
So we're just getting all the models.
Yeah, I don't see the exact connection though. Yes. We're getting all the models that satisfy these axioms, but then we're identifying a bunch of them so that we get basically one consistent model at the end. Yeah. That
makes sense. And then the second question is, so we could characterize the independence of the continuum hypothesis, for example, as being outside of the ultra filter that was generated by ZFC. Right? So if the axioms of ZFC...
Well, okay, so... Yeah. So the thing is, maybe, potentially, but you also have to always remember that you're always doing it with respect to a bunch of models that you had before. So I'm not sure when you're taking like models of ZFC, what models are, because ZFC by itself is not a model. ZFC is just a list of axioms, right? The model is something that makes those axioms true, but also like has a physical, you actually know what it is. Like you have to explicitly a model.
You have to construct it.
Like implied.
Right.
You have to construct a model, yes.
Yeah, but exactly. if you did have all these models, if you had a bunch of constructions that satisfied ZFC, you could form an ultra filter, and then any independence, it's not just ZFC, but any independence result means that statement is not found in the ultra filter or in the resulting ultra product.
Maybe. I'm not sure though.
Okay.
But
just speculating here.
Yeah, I'd have to think about that. Yeah, obviously girls' completeness is extremely relevant to all this. I didn't add it in just because I already had so much. But the one thing about like proving independence of the axioms from the continuum, basically what Gödel did is showed that there exists a model of ZFC such that the continuum hypothesis holds. Okay, that's what Gödel showed. What Cohen showed with forcing later was stronger, was rather than sort of Gödel is actually, this is actually maybe an important point, going back to this Wilhelm theorem, that what Gödel did is basically model that has a continuum hypothesis. And what Cohen did with forcing is he started all models, added enough sets so that you actually had more infinite quantities. And so he actually forces the continuum hypothesis to be false. But I didn't go through the exact details of it. This whole thing to make the continuum hypothesis true, you can do this with exactly with this ultra product construction. You also, if you take something you might see rather than the ultra product, the ultra power is if all of these models are the same model. It's the product over the same model modeled out by an ultra filter. I know this is used to often to construct the non-standard reals. Sort of, I guess, as I showed before, you can also use an ultra power over a certain filter.
Mm-hmm.
And finally, I just wanted to add, this is the big theorem. This is Losch's theorem. So this is what actually gives you forcing on model theoretic forcing. It gives you conditions for how you can do it. So if I have, okay, so I have this ultra product, which we just constructed. Then for every formula phi and alpha 1 to alpha n in the product, right, that each one of them is going to break down into a product. We have that it's going to force, remember these, because in the product we're taking, these are really the equivalence classes. Each one of these bar to the one, the little outside thing with little brackets. So we see that the model is force this, or models this sentence if and only if the set of indices such that this submodel mi forces applying to just coordinate is an F. So we get that relation between actual forcing and things, the various indices of this set being in the ultra filter. So I actually think this is close to what you were asking, Gabriel, right? Mm-hmm. That you want an axiom. The indices of the model that force it should be in the ultra filter, or of the submodel that force like restriction of it. So it gives you a way that if I have one of these ultra products, I can explicitly look if all these axioms are if they're satisfied. So Losch's theorem, what it does is it says I can take a bunch of models that individually maybe have satisfy different axioms, and I can glue them all together, basically along an ultra filter, identifying certain things in the ultra filter, and get a new model that satisfies all these things, that adds an axiom that really, and we can concretely say what the axioms are and what things it satisfies. So this Losch's theorem, this is kind of the central theorem of model theoretic forcing. It's what gives you like the necessary and sufficient conditions. Yeah, and that's the last slide I have. I don't know if there's more questions about this. This is a doozy a bit.
Yeah, I'm trying to get my hand around what I'm seeing. Yeah, okay, so Losch's theorem is saying that if you are able to do this ultra product of the models, that this ultra product itself, like this so the model that is this ultra product, right? This is what the first line here means.
Mm-hmm.
Right? The model that is defined as this ultra product is such that you can force this new proposition in this model is equivalent to forcing it in each of the models that were filtered.
No, sort of. It's saying that these indices, right? So the models, the indices of the models,
Mm-hmm.
that force the proposition should be in the ultra filter. So it's about them being in the ultra filter.
Okay.
So whenever the models,
the crucial part is here.
As long as all of the submodels of this product that satisfy whatever axiom or proposition you're concerned about, if that is in the ultra filter, then it applies for the bigger model. So this is this whole gluing. So this is really, I want you to think of this very much similarly to how you can do it, for example, with like a topological space or something. So maybe it's just to draw an example. This is not going to be about models, but for example, right, you can take, if I take, right, R2, okay, what's R2? R2 is really just, it's the real numbers, producted with the real numbers, right? Okay, so this is already a product. I'm just trying to give it a little bit of an analogy, so maybe it's not exactly the same, but if I want to construct a surface, so imagine if I want to construct a torus, okay? What can I do? I can say that there's going to be a relation on this R2 such that, let's say X, Y is equivalent to A, B, right? If and only if. We have some integers. What letters should I use for integers? I and J. Okay, so these are integers at X plus I, Y plus J equals B. Okay, so what's this saying? This is saying if I have a point, and if I liquid, right, generated by this point. So I have a grid of like the integers that are all right, like this little lattice thing. That each point is going to be equivalent to this point. It's going to be equivalent to this point. Anytime it differs in either or both things, entries by an integer. Okay. So what do we get? We get all these identifications. But really, we can just look at this one square, and we can actually see that, like, right, let me change. We can say that, like, this side, right, is going to be identified with this side, like this, because all of these points on this edge are going to be the same there. Same way, the other way, this side is going to be identified with this side. So you can imagine like gluing this, right?
Yeah.
If you glue this, the green edges together, and you glue the blue edges together, you get a torus. That is not letting me draw. There you go. You get this where, if anyone hasn't seen this before, blue edge is going to be like this one going around here, and the green edge will go around here. But I really want you to think of this as sort of similar to this situation, right? It's taking something that we understand. We understand the real numbers. We're doing a product on them. So we're looking at them together, and making a larger space out of this simpler space that we understand. And then we're putting a relation on it. In this case, this relation is this one, differing between integers. In our case, the relation is, where is it? Here, this one, where the indices where they agree is in the filter. Okay, we're using the filter and a equality on the as a relation that we can do the same kind of quotienting where we identify elements together. So
okay.
to think of this in the same, but just like be wary that while, for example, with a space, it generally works out, the quotient works out nicely and you can kind of fold it into a nice manifold space. It's more difficult here because models and axioms are much less well behaved than kind of standard mathematical objects because they have this kind of weird meta-mathematical stuff happening in the background, and you got girdles, completeness, and whatnot to worry about. But yeah, I hope this was enlightening and maybe showed a bit of how model theory actually works. Beji talks about it quite a bit, so hopefully it'll help you understand that in context more. So
for me, it helps a lot, but it's also, I mean, the fact that this last step, I mean, it seemed to me like you went all the way to ultra filters, exploring, let's say, this space, like the emphasis was more on space than on logic, though we mentioned, can you guys hear me okay, though? I mean, my connection is a bit dry. Yeah, okay.
Yeah.
But exploring more, I mean, you touched on the fact that you can treat filters on propositions and not on spaces, but we were mostly dealing with space. And then we stopped and we started constructing a separate venue with models, and which is focusing more on the logical part and the idea that models are somehow like this propositional spaces, right, where some structure holds. And this point here is suggesting that the result that we found concerning ultrafilters actually applies to models themselves.
Which result about ultrafilters?
The whole point about, I mean, not the result itself, but that you can apply the strategy.
Oh, the lesson,
the general properties of ultrafilters can actually be kind of recovered and put to use in the discussion of what like these propositional spaces are, right?
Yeah. So where the ultrafilter comes in, right? Here, it's what guarantees this like global consistency between all of these producted models, right? Because we talked about how the ultrafilter gives a map global consistency. So basically, it decides everything on it. So we're saying that ultrafilter is going to it decides everything, but what's it deciding? It's depending on if these indices of I are the models that force propositions. So it's deciding which models and which forcing relation models are going to be counted and are going to be determined to be true. It's difficult to, I guess, give like an intuitive explanation for how this works, just because first of all, there's so much literature about this, like almost unpenetrable, even when I spend many hours on it, and I do that all the time anyways. But it helped a bit. I'll send you guys that paper. Let me actually find it right now.
So I'm not sure.
Hopefully a lot of what I was talking about is sort of based on that. Go ahead.
So I'm not sure if this question's gonna like actually fit, but just trying to understand it. So going back to even before when you got into filters, when you were talking about Yanida, and you said that the kind of one of the big philosophical takeaways was that in order to really use it, you need to have a class of relations that both enables you to cover what you're studying and then also differentiate. Where does the coverage and the differentiation kind of fit into this place that you end up?
In the case, in ultrafilters. So actually, let's just think about that for a second. Ultrafilter already sort of what it does is it's covering the space with truth values in a way, as much as it can. I want you to think of the ultrafilter as the set of things that are going to be true. And once you have the set of propositions that are true on the ultrafilter, if sort of the space that this ultrafilter is based on is expressive enough, then the ultrafilter will sort of be deciding all of the propositions of the space. I don't know, the thing is, ultimately the whole thing about like deciding the amount of relations you're talking about doesn't really come into play with the filter, just because an ultrafilter is always in relation to an ambient set. It's always an ultrafilter on something. So that point that you made is that whenever I'm looking at a model in the first place, or thinking about what models I'm going to consider, you want to take into account enough of them to cover the space. So this being, I guess, a lesson would more so be applied on the set of models that you're choosing. And the ultrafilter is something that comes from basically the axioms that you want. If you're trying to like force it to maybe obey certain axioms, the ultrafilter is how you take those axioms, you complete them to be a filter, and then you can use the ultrafilter theorem to extend this to an ultrafilter. That might not be unique. There might be different ways to do it. But as long as you have all the axioms that you want in there, it will be a model for this, for those axioms either way. Does that make sense? Hopefully.
So does this enable you to verify whether or not the sets you have chosen are adequate then?
Yeah, I mean, so knowing whether the sets you have chosen is ultimately like I think it's like a heuristic kind of choice, right? You can't really know within the system if it's enough, because you can choose these sets, you can do a bunch of stuff in them. Everything can be completely consistent in everything. But maybe if you want to use it as a model for some kind of like space of value or something, or whatever you want, you don't sort of within those themselves, you can't really determine if they're sufficient, because you have to connect them to something outside. So you really want to make sure you have, in this case, if you're doing this ultra product thing, you have to make sure you have sort of enough of these models and that the models are expressive enough. But yeah, in general, it's all about context. It's about understanding, right? So like, none of this stuff by itself, I would say like, gives you anything new in terms of like axioms or anything like that, but it gives you tools by which to work with the models you have and to understand how they work. But ultimately the choice of like how many models, what is important, that's like a heuristic choice that you're going to have to, it depends on whatever the context is. But the lesson from the whole Yoneda thing is that you want to make sure that you choose enough, a big enough space, enough relations to cover your thing sufficiently, but also that it can, I guess, differentiate different. So not just have a lot of stuff, but you have to have the right like fine-grainedness. And this is about the whole question of scale. You're talking about like connects.
Yeah, I mean, one thing that I think it's interesting to highlight is that one very central issue with these things is what you can express inside some space. And I think that this issue, I mean, Dennis mentioned the whole thing with Gödel and so on, but one thing that I think is very, very useful in general as an intuition and as a sort of underlying kind of approach to have in mind in trying to extract something from this for the project we're dealing with is that the fact, I mean, moving totally outside of mathematics towards like economy, organization, and social life, and so on. one of the issues is precisely, let's say, what is possible, like, what are the machinery allowed in a space where you cannot see everything, where you cannot see the whole? What are the things you can do locally?
Yeah.
That tell you something about the whole, right? So, for example, if you're able to, for example, if you can verify, to go back to something he said very, very early on, if you can verify that everything that the coverings of this space all intersect on the same thing, and that space is infinite, then you know something about its global structure, right?
Yeah.
That's a way of talking about, for example, very loosely speaking, about price, which is the idea that, well, insofar as everything is priceable and price relations are consistent with each other, then you know something about the global space. That's, let's say, a way to say that price is a way of covering the social space that gives you an immanent measure of that space. So when we talk about the possibility of other ways of social coordination, of course, you can simply think about a substitute for price that respects the same conditions. But I think what Yasha shows is that you're not obliged, like there's not only one way or one formal strategy to have access to properties about the global space from the coverings. You can actually come up with alternative ones. I think that the flashy difference is the one between a principal ultrafilter, which has the same, everything intersects as the singleton, right? But you can imagine, you can formally prove that it is possible to have a different way of covering with the empty intersection, but you can extract something about the global from this different way of covering that space. But that doesn't, like, how that appears locally, right? Or what you need to be able to do locally so that this is verified, right? That's the tricky part. And so what are the preconditions so that other ways of doing this is possible? I think that's the tricky part. And I think that the fact that you can approach all of this from a propositional way and from discussing, let's say, what can be held to be true locally and how you can actually stitch together true propositions, right? Even though you're varying the axioms that make them true between models, right? That actually gives you a kind of in-between, formalism to arrive closer to the problem, because turning from spaces to propositions, it brings you closer to something, for example, that you can translate into economic theory or those discussions. For example, propositions in economic theory concern things like X is worth Y of something. So supposedly you can guarantee the consistency of some space of value relations because you can translate everything into terms of value propositions. Like this is worth as much as that, right? So one way of approaching all of this is saying, okay, you know that there are weird mathematical crazy structures that formally prove other ways of stitching things together can actually give you access to some global information. What forms of proposition, right, or predication of a situation might be able to hold alternative to X is valued Y amount of something, right? That allow you to also cover the space and know by only the local means of expression that you've touched on something that has global value, right? That holds globally. So
yeah, exactly.
Okay. Yeah.
Yeah. So that's a simple problem. Let's solve that and get world peace. And
yeah. A better conclusion than I could have done myself.
But it's totally crazy, man.
Is that everything? Well, yeah, it is very crazy.
Yeah, and I also like that you guys use the value space as the target example, right? Like we're kind of on the trail of this. How do we conceive of models of this space? Yeah, or maybe this space.
That's what I wanted to keep mentioning.
Yeah, you mentioned it multiple times, so it's really good. It's very evocative.
Yeah, I mean, I think it's very applicable. So yeah, we'll see if we can use any of these tools. Maybe not even directly, but maybe indirectly. At least, even if, okay, this is one thing I'll say. Even if like all this formalism is kind of like garbage and you don't care about it, which is totally valid. I think there's a few lessons, right, you can still take away from this stuff, this whole meta lessons in philosophy about things and their relations determining the size of the space. I think it's really important. And also, actually, this down theorem, just because it sort of always guarantees that there is infinity that is larger than the model that you're always working in. There's always a point of excess, which for philosophy is a very
that's actually how Badiou calls the Lovenheim scaling theorem in being an event, right? The point of excess.
Oh, really?
Yeah.
Oh, wait, does he in the third book? Does he mention being a?
Yeah, he does.
Ah, okay.
But one thing that I think it's a good kind of segue for all of this, that, I mean, this is something we'll try to present tomorrow, but one thing that I think we realized by rereading Capital recently, Dennis and I, is that we know Marx writes, can I just share the screen really quickly here? Marx writes go for it. This very, very famous discussion on the form of value, right? Which is like some amount of a commodity equals some other amount of some other commodity, right? But then you see that, like, to arrive at the money form, it's not a matter of simply realizing, like, first that you can compare one commodity to a bunch of others, right? And so on. But actually that you can express all of these commodities in terms of the first, right? So you know that then he writes the inverse like this.
Mm-hmm.
But then when you see the way that he expresses this, he shows that this is not equal. These two things are not the same, because there is actually a predicative structure hidden behind this equality. This is not extensional equality. This is actually a way of phrasing. This actually means something like x of y is worth y of b, right? So
but it doesn't go the other way around.
Yeah, the other way around doesn't function. So what actually this is doing is saying that you can express value as a commodity, a specific commodity. So you're saying, like, there is X amount of A in B, right? B is X A, like A above, right? It has some A-ness to it. So he's actually treating this as a sort of predicate. And you can actually ask, like, how much a certain commodity C, how much A is it? Like, how much of A it is? Like, or how much of A you can see in it, right? But that's actually like a predicate structure, right? This means that for the money, you have some commodity here. C means that C belongs to M in some level, like, which is like the atom definition for Badiou, right? As if M is a predicate that defines some set. So it's actually very close to a sort of predicative description. Like, money is sort of a predicate that applies to everything, right? So I mean, this is where we're going now. So I think it actually comes close to this idea that to define the money form is to define some way of predicating about economy where everything can be expressed. Supposedly all properties about stuff can be expressed in terms of that predicate, right?
Yeah.
So there is actually...
Maybe we can actually say, using this presentation, that every commodity is a principal filter, but the money commodity is an ultra filter. Right?
I mean, that's what Baidu says, right?
Yeah, that's basically what we were interpreting.
For capital, but yeah.
But we can find the intermediate step to get to Baidu by saying that before we have the ultra filter, each one of these predicates serves as kind of a filter, a principal filter. Because from the perspective of any commodity, not necessarily the money commodity, but any commodity, it's filtering the world for its A-ness, like you said, right?
Okay, yeah, I see. Yeah, so I define
so you can
commodity.
measure anything in terms of a particular commodity.
Yeah. I fix this commodity, and then I can see some amount of this, I can see some amount of this other one, right?
Yeah, exactly.
So it gives me a slice of B, Z, and so on.
Yeah, and I mean, the filter structure, yeah, exactly. You have the union of X, B, and Y, Z above this, right? So it's closed upwards in that sense.
Yeah.
That Yasha was describing.
Yeah.
True.
And
so
some commodity can, So if some commodity, right, can differentiate everything too, that would be like the principal ultra filter, and that would be like a money commodity. If it can differentiate everything in the, I guess, like space of value, space of things that we give a price.
So then the inversion here, where all of these things are in terms of this is, we are saying that this then is an ultra filter.
If we consider, we have to define intersection and union in a sensible way, but yeah, if we could say, I mean, Marx does this, right? When Marx says that things are exchangeable because they are products of labor, he's implicitly saying that there's a something there in the conjunction of the world of commodities, right? Every commodity, if you do an infinite conjunction or an arbitrary join, right?
Yeah, they all have labor.
They all have labor at the bottom.
The abstract labor, though.
Yeah. Abstract labor, right? Which gets turned into the money.
Yeah.
But then, so then that predication would at some point would move back into an equality at the level of abstract labor, right? Because we're talking about an equality of labor time.
Yeah, I mean, we're actually going to try to deal with this tomorrow, because I actually think that there is a nice subtlety between money form and money commodity. And one way of thinking about this is to ask like causally. All commodities can be valued in terms of money. Therefore, there is some kind of homogeneity behind them, and therefore I should find this homogeneity at the production space prior to the homogeneity on circulation. So you get that classic debate: what comes before, circulation homogeneity or production homogeneity, right? And I think that the way we're approaching this, and we'll try to present it tomorrow, kind of does away with that problem a bit, because if this predicate that you found, this sort of money predication, it's or you could call it priceability, the possibility that you can split up any object in terms of its priceable parts, right? If you can decompose an object in terms of its priceable parts, you're actually decomposing the object in terms of the way it is produced in commodity producing labor. Because the priceable parts are the prices produced in capitalism, right? So it's this mereological distinction between the money commodity, the object money, and the money form as the predicate that slices objects up based on priceability, right, as an atom.
Mm-hmm.
It actually splits between circulation and production, kind of like organically, because relations between objects concern circulation, relation between parts and wholes concerns production. So you never need to ask causally what comes before. It's just one thing. Like if you can splice an object, split it up in terms of priceability, you already split it up in terms of capitalist production. So you never need to ask like what's special about labor? Does it have an ontological special character to arrive at what makes it homogeneous, right? You can define it logically and not ontologically. But I think we'll try to make that clear tomorrow. But it's a side problem, but it's very much connected with this way of thinking about the money form, right? The possibility of localizing all the parts of an object in terms of their expression in money.
Yeah.
But I think we'll manage to get there tomorrow. But I think it's very interesting, this point you guys made about the filter and the ultra filter and the two parts of the value form. That's really, really amazing.
Yeah, it's amazing that this presentation fits exactly in that part. Yeah.
Nice. Nice. Yeah, we'll have to try to develop that idea more. But
no, of course,
there's definitely a kernel of something good there.
Yeah. I think just feeling like we're touching on something good is, it already suggests we're on the right way.
On the right track, yeah. All right.
Thank you so much, man.
Yeah, thank you. Great presentation.
You're welcome. This was fun. Thank you. Well, I'll try to listen in tomorrow if I can. Okay.
So I'll send everyone the link tomorrow.
Yeah, sounds good.
See you guys.
Take care. Bye. Good meeting.